Bruce Wexler, MD, is the Professor Emeritus of Psychiatry and Senior Research Scientist at Yale School of Medicine, and Director of the Neurocognitive Research Laboratory at the Connecticut Medical Health Center. In 35 years of neuroscience research, Dr. Wexler has advanced the understanding of brain plasticity and been an international leader in developing computer-presented brain exercises to treat cognitive defects in people with psychiatric illnesses. His patent-pending innovations led to the development of the Active Cognition Cross-Training Program for children and adults. Today, Dr. Wexler is sharing with us about ADHD and ADD. Dr. Bruce Wexler.
Thanks. Good morning. I want to thank Drs. Minsons and Potter for really excellent presentations. This was what you would get at a world-class scientific conference. Very great science and very clear presentations. I learned a lot already today. I'm going to be talking to you about attention deficit hyperactivity disorder and other problems with executive functions. As you heard, I'm a professor at Yale University. I'm also a founder and an equity holder in a company, a Yale startup company called C8 Sciences that creates and distributes the brain training program I'm going to describe in the latter part of my talk. So I want to disclose to you that I have those financial interests. Children with ADHD have problems with attention. It could be mind wandering or being easily distracted. They have problems with self-control, waiting their turn to speak in a conversation, waiting to be recognized by the teacher if they hold up their hand. They have decreased memory. Together, we consider these functions part of a broader suite of cognitive operations called executive functions. Executive functions are essential for managing information, managing ourselves, and being successful in the world and in school. Three fundamental executive functions, foundational ones, are focus, self-control, and memory. Ability to focus and have self-control when you're in kindergarten or first grade predicts how well you'll do in math and reading throughout your school career. If you have attention problems when you're in third grade, you're nearly 8 times as likely to fail to graduate from high school. And we've already heard the consequences of that in relation to children with dyslexia, underemployment, unemployment, drug use, jail time. These cognitive functions are better predictors of success in school than IQ. So the problem that we need to address is that 17% of all elementary school children have serious enough attention problems to put them at this risk, 7.6 times greater risk of not graduating from high school. This was a study of 2,000 children who were followed for 16 years after assessing their attention skills in third grade. And 17% of that general population fell into a high-risk group of poor attention with this level of risk of not graduating from high school. 6.4 million children in the United States are diagnosed with ADHD. The cost to schools, to families is, of course, very high on the personal level, also financially. ADHD can be missed. It can be an invisible disability. The mind-wandering type of ADHD, not every child with ADHD is hyperactive, so it is an invisible disability in some cases. I'm going to introduce a number of different terms to you during my talk, so I don't want you to worry about having to keep track of them all. So I'm going to give you a review periodically of the terms I've just introduced to make sure we're on the same page. So I've talked about ADHD, about 6% of children have it. I've talked about executive functions, a suite of cognitive operations. Foundational in that suite of cognitive operations are focus, self-control, and memory. And then I've talked about another term, serious attention problems, that 17% of children have. So we've got a group with ADHD. We've got a group with serious attention problems. The same study found that another 18% of children had significant attention problems. That's 35%. How do we think about this? Is this just a continuum? Does everybody really have the same problem and some, it's diluted a bit? But it's just, and that's why they have less severe form. It's not quite as strong, but it's the same problem all along as a continuum. Or are these a group of different disorders, different situations? And I'm going to explain why it's important how we think about that. So what do I mean about different disorders? We could have the clinical diagnosis of ADHD being one distinct entity, serious attention problems being another diagnosis or entity, and then milder attention problems being a third one, sort of a continuum, but broken into discrete groups that may be different from each other in important ways. So let's say they are distinct groups and importantly different from each other. What about inside of each group? Inside that ADHD group, for example, are all those children the same? Do they have the same problem? We would call that homogeneous. So we've got three groups, but they could be homogeneous, meaning that if you're in that group, clinical ADHD, you all have the same problem. If you're in the serious attention group, but non-ADHD, you have a different problem, but you're all the same, and so forth with the attentional weakness. Or it could be, even though we've said now we've got three different categories, when you look inside of them, the kids aren't the same, even though they have the same label. So here we have clinical ADHD, and you can see they're all different types of problem inside that clinical descriptive category. Serious attention problems, the same, mixed. Weaker attention problems, the same. So the answer is, we are faced with this problem. We have a continuum behaviorally. We'd like to divide it into discrete groups if we could, because that could be important in ways I'm going to explain shortly. But if we try and divide it into distinct groups based on a description of symptoms and behavior, each of those groups themselves is not homogeneous. It's a mixed bag of children with all sorts of different problems who just happen to look the same on the surface. So I think you can imagine where I'm going with this. Because we want to be able to treat people, we want to know what's wrong, right? And if you look at a behavioral description, a clinical diagnostic category, it doesn't really tell you what's wrong. And that makes a challenge for us to figure out how to best help a mixed bag of children. So, ADHD, we've got that down. Executive function, serious attention problems. Now this concept. Are these homogeneous or heterogeneous categories? They're heterogeneous, within each one a mixed bag. And now the question, well, what's the cause of the underlying problem for each child? Because, how many of you have had this situation? Your car breaks down, you say, I know what to do. You get out and you open up the hood. And then you stand there and you stare at the engine, right? Because you really don't know how it works, first of all. That's one of the problems we have in psychiatry. We don't know how the brain works. It's a lot harder to figure out what's wrong with something if you don't know how it works normally. But we don't know what's wrong. So you're looking at your car, it's under the engine, but that's the end of it. But if you did know how it worked, like a mechanic, or some of you do know how your engines work, you can make that diagnosis and fix it much more quickly. So what do we know about the etiology or cause of executive function problems like ADHD? And you've heard in these first two talks the same line then of logical and scientific inquiry. Both the speakers described to you a clinical disorder, and then they started sharing with you the efforts to figure out what's underneath of it, what's causing the problem, so that the treatment can be focused, directed, and effective. So some children have neurodevelopmental disorders. Genetic factors are relevant, and some of them, we don't know what they are yet, but they are relevant. There could be toxins in the environment or in foods that could contribute to some children. We do know from brain imaging studies that some children with ADHD have slow and incomplete development of parts of their brains that are particularly important for these executive functions. That's the reasons that some children grow out of it. That part of their brain can catch up. It's just slow in development. It causes problems for them. Those problems can then create other problems. That's what we'd like to avoid, while their brain can catch up and develop. And then there's another very important source of problem, and this was alluded to in the previous talk. Our brains develop from stimulation after birth in the real world. Literally, structure and function of our brains develop after birth from stimulation in the world. Some children don't get enough of the right kind of stimulation to promote development of the neural systems that support executive functions. They're put into school, demands are made of them through that no fault of their own they're not neurocognitively prepared to meet. And it sets off a deviant developmental trajectory of great cost to them, their families, the school, and society because of that mismatch. Many of those children come from poor and disadvantaged backgrounds. Their families don't read to them, don't have time to read to them, don't know how to read. It's not part of a hobby or an interest or part of their lifestyle. Even worse, some of those kids are exposed to trauma. And through ways that we don't know, exposure to trauma, even just witnessing trauma, further compromises executive function. I can't tell you that mechanism, but that's part of the picture that impacts large, unfortunately, portions of our population. Okay, so I've given you a rough overview of the size of the problem, how many kids have attention problems, the complexity we face because we don't know how to categorize them, and if we do try and categorize them, we already know that inside the categories, there are all a bunch of different problems we have to treat. I've said some things about different types of etiology that could be contributing or probably are in a different mix in different situations. So what are the treatments? There are medications that affect brain function. In the first talk this morning, you heard about the effort to develop chemicals that can change the chemical process in the brain that leads to Alzheimer's. That's one way we try and intervene physically. There's family therapy, very important for children with ADHD. It disrupts the family ecosystem. A lot of negative interactions. Parents don't have the skills and patience. Couples then don't get along and work as well together. That's a point of intervention that can be very important for families and children's happiness. What I'm going to focus on now, in the rest of my talk, is another form of treatment. It's cognitive skills training and brain training. It harnesses neuroplasticity. We didn't plan this series of talks this morning the way they are, but you can see that the themes are recurring from one to the other because that's where the cutting-edge science is right now in trying to understand more about how the brain works and use that knowledge to help people. And neuroplasticity is a big part of it. Harnessing neuroplasticity. We want to be able to train and improve those same three cognitive executive functions that are so important. We know they're important. We know they predict success in school. We know some kids don't have them. Why wouldn't you focus on that and train that if you could? It's not teaching them math. It's not teaching them reading, but it's preparing them to learn. And what we want to promote is what we call activity-dependent growth of a targeted neural system. Once you know what's wrong, once you have a target that you can address, we now know enough that we can do something to that neural dysfunction through activity-dependent growth of the targeted neural system, just like you heard about in the last talk as well. Cognitive training is really, in my mind, pretty much the same as brain training. How could we be training cognition without affecting the brain? Well, I just got a letter from the communication from the editorial office about a paper of mine that's under review. Could you please change the title and not use brain exercises? You didn't do brain imaging. You only did cognitive training. Why are you calling it brain? So I didn't argue with them. At that point, you just want to get the paper out there so the information can be shared to say, well, excuse me, how is it that you think I'm improving cognition if I'm not affecting the brain? But that's not an argument to have. but we know it is. So you've heard a little bit already about neuroplasticity. It's in your programs, that great quote, neurons that fire together, wire together. How powerful is that? It is extremely powerful, and I want to show you just a couple of examples quickly. This is what happens to your brain if you practice music for many hours as a child. And what I want to draw your attention to first here is this, in this circle, you can see the volume of the sensory motor cortex in the left side of the brain, which is controlling the right hand. And if you're a violin player, what does your right hand do? A relatively simple, repetitive motion like this. So that provides us a little scientific control built in. Because we're going to say, well, what happens to the brain that's controlling the left hand, that's learning all these very fine, quick, fancy fingering movements? So look over here at this side of the brain, the right side that's controlling that left hand. You can see with the naked eye the volume expansion in this side of the brain compared to that side of the brain, because there are more connections between the neurons. There could be more recruitment of more neurons into that functioning system. If you look at a piano player, they use both hands, right? You've seen those kids do it like with their eyes closed. And the prodigies on YouTube. Amazing, yeah. Two of these buffed up motor cortices, both sides of their brain. So people are harnessing this neuroplasticity now for therapeutic purposes. One of the things that most impressed me is the ability now for blind people to see through their tongue. How many of you have heard about that? What they do, originally, what they do is they make spectacles with a camera on it. Now, if a camera sends a picture to a TV screen, how does that work? Little pixels, right, everywhere? And some pixel gets no light, and some pixel gets a bigger, more intense light, and you can make a picture that way, a representation of the outside world. So the first thing they did was make like a TV screen on the person's back. And instead of light going to every little pixel, it was a little electrical signal. And if the electrical signal was intense, that's like a strong light. If it's weak, it's like a white light, soft light. And if nothing is there, no light at that particular spot. And they said, we don't need to use the back, we can use the tongue, because the tongue has so many neurons that in a piece of metal this big, we get as much resolution, as many neurons as we could get in the whole back. So they put this little device inside the person's mouth, and the camera on the outside sends signals to it like a TV screen. And the brain, how's the brain deal with that? Brain doesn't care. If the input's coming from the retina, which then sends an electrical signal to another place in the brain and then comes up to the visual center, what's the difference? Electrical signal's coming from the tongue, sets another signal up. The brain quickly realizes, hey, information is coming in from the tongue that's telling me about the outside world, and it can process that. Everybody in this room in 5 hours of training with this could learn that basic reading chart. You could see whether the 3 lines were pointing this way, this way, this way, or this way, through your tongue with 5 hours of training. That's the neuroplasticity. That's the potential we have to harness. There's somebody rock climbing, with a blind man with this device. He can see well enough to know really where to put his hand. Doesn't have to just feel around anymore as he used to. Okay, some more terms. We've still got ADHD in mind, executive function, serious attention problems, homogeneous or heterogeneous disorders we're dealing with, but we want to figure out the etiology so we can get better treatments. Hey, neuroplasticity, that's something exciting about the brain. Can we harness that for treatments? And now I'm going to talk to you about a specific treatment that we've developed, a whole program to harness neuroplasticity, to improve executive functions, a non-pharmacologic treatment for ADHD, but also a broader application to children who have attention problems, perhaps because they come from disadvantaged backgrounds and have not had the stimulation to develop those neural systems. The program is called Activate. One of the things that distinguishes it and we'll talk more about this from other brain training programs or other computer game exercises, is that we have both computer-presented and physical exercises integrated together. Also very nice to hear in the last talk about the importance of physical activity coupled with another type of direct brain stimulation. And our programs focuses on improving focus, improving self-control, and also improving working memory. We have three components. I told you about two of them: computer-presented brain training exercises, physical exercises, and also assessment. I'm going to talk to you about each one a bit and then show you some data. I will say I don't have time to get into the details of the functionalities of our programs. I've been working on developing them at Yale for about between 15 and 20 years now. So we're next generation or third or fourth generation programs. Just as a quick shorthand validation, our program was evaluated for the director of the National Institute of Health by an anonymous expert who said that our brain training exercises, quote, were easily the most sophisticated ever conceived for any disorder by anybody. It's because we worked at it for a long time, and they're sort of next generation programs. They have a number of features of real-time online error diagnostics that figure out what type of mistake a child is making, when the child is making it, and give them feedback right away. And also algorithms that enable the programs to more quickly and accurately individualize the challenge level to each child's ability and focus the training time on areas of their weakness rather than their strength. Very important if you're doing large-scale applications, as we do in classrooms where you have teachers who aren't really trained in this and you've got 30 children in the classroom. They can't customize the way the computer can. We customize in real time, individualize in real time. We try and make the games interesting and engaging. I'm just going to show you some of the screenshots. We give the kids choice each day. We have a booth outside so you can actually try the games. But I'm also going to say something about what these games are not. Because some people say, oh, well, there are lots of computer games, and we think our kids are doing too many of them. And some of the kids say to us, well, these computer games are not as much fun as the other computer games we play. So what these games are not, they are not the high stimulation, high arousal, arcade-like entertainment games. Why not? Well, children with ADHD do those all the time, right? So what's that tell us? One, they can do them. It's not challenging their deficit area. And what else does it tell us? It's not helping them get better, is it? So why would we make games like that? The kids want us to, but why would we make games like that? Obviously, it wouldn't be therapeutic. The entertainment industry makes games with one goal: get the kids to want to do them more and more. Many of them actually bypass the executive function systems that require self-control and effort and actually engage through the neural systems that are very similar to those connected with addiction. And that's their goal. But we have to employ then other features to try and get the children to like and engage with us in our games. We do all right with them. I mean, one of the nice things, what we can do now, we have a completely web-based platform and 5,000, 6,000 kids using the program across the country. We can actually ask the kids, how do you like the games? Not only is that good feedback, but we can make a change in the games then and test it within 3 weeks to know whether it's making the game better or not. You can see the turnaround, iterative turnaround for improvement of this type of intervention now when you couple it with technology, computer technology, and the internet. So anyway, we were wondering, let's get a baseline of how much our kids like our games. So this was in 3 weeks. We had responses from 1,264 kids, and there you can see the smiley face ratings. We're doing all right. 2/3 of the kids were smiley face, and we say to ourselves, you can't please everybody all the time, but we do want to please more if we can. Okay, so the physical exercises. The key thing about the physical exercises, they're designed with cognitive components, so they engage the same neurocognitive systems as do the computer programs, but now in the context of whole body activity and social interaction. There's movement in schools to restore more PE time. I think that's very important, and we can help that process because we are actually showing, providing added value for the PE time because the exercises, the physical exercises now actually integrate with primary goals of the whole curriculum for the school. This just gives an example of them. Just like the computer games, the physical games, exercises start with simple functions like sustained attention. For this, it's just, this is my space, self-control and attention. That's somebody else's space. This is my body. I can concentrate on my body to do different movements. But then we have social group games that require memory, sustained attention, response inhibition, cognitive flexibility, things like that. Okay, so I said there were three components, right? Computer programs, physical programs, and assessment. Assessment, measurement, the foundation of science, the foundation of evidence-based practice, whether it's medicine or education. If you can't measure, you can't tell what you're doing. Most measurement of cognition up to now, where's it been done? It's been done in neuropsychologist's office, in the laboratory. What's the problem with that? Well, one, obviously cost. Full battery, $5,000. Impossible for most kids to get it. Second problem, the child is being assessed when they're sitting next to an adult in a quiet setting. That's not what happens when they're in the real world. We have created tests and enabled teachers to give these tests to a whole classroom automatically, no special training. I'm writing a paper now with 24,000 classroom administrations of gold standard research tests of executive function and showing that we get valid data on them. This is one, it's called the flanker test. You just have to push up on the keyboard the arrow that's pointing in the direction of the center arrow. On easy trials, all of them are pointing in the same direction. On the difficult trials, the flankers are pointing opposite direction to the one in the middle. It slows everybody down, so we measure reaction time on these incongruent trials, they're called. This is data in the classroom from children with ADHD in red and non-ADHD children. You can see at baseline, the ADHD kids are slower. So we have a test that's picking up the deficit in the classroom. And after our training program, over 4 to 6 months, the ADHD kids have erased the deficit compared to healthy kids. Here's a response inhibition or self-control test. Once again, you can see that the ADHD kids at baseline are below the typically developing kids. Again, validates we can measure this in the classroom setting, and they start to close the gap after our training. So, formal NIMH-funded study of children with ADHD. We used parent ratings of their symptoms to tell us whether they were getting better. Do you think that's a good idea? Parent ratings, would they know? Some people say yes, absolutely. What do most scientists think? We don't want parent ratings. They're biased, they're not scientists and stuff like that. Well, turns out that parents see kids much more than anybody else. ADHD manifests itself differently in different settings. Parents have some important information. According to parents, children who got our program were twice as likely to show a significant improvement than a control period. But it had this problem, right? That some people weren't sure about parent ratings. So we took it another step. We said, let's look at the kids whose parents said they got better and compare their objective cognitive tests, I've just told you, to kids whose parents said they didn't get better. And what did we find? That the kids whose parents said they got better showed highly significant improvement in all our tests of focus, self-control, and memory. And the kids whose parents said they didn't get better showed no improvement. So the parents were right, first lesson. Second lesson, not only did a significant proportion of kids get better in their symptoms, they also got better in their cognition, their executive functions from this training program. No medications involved. This is a quick slide of what happens when you do this brain training program, our program, in kindergarten, and then you look at the kids when they enter first grade. A naturalistic experiment. We had first graders, we were assessing them again. Some had done our program in kindergarten because they were in a kindergarten that gave the program. Other first grade classmates sitting right next to them getting the same test at the same time were not in a kindergarten that had done our program. And the higher blue bars are the significantly higher performance, greater strength and focus and self-control at the beginning of first grade of kids who had gotten the program in kindergarten. This is school readiness, and it's carry over the summer, which people are worried about. This shows you data from over 1,000 children, K through 3. On the graph here, what you see in the blue bars, these are our same tests now of focus and now working memory. What happens if you give the test twice after only 25 minutes of training? Do they just get better because they've done the test twice? That's the improvement, 2%. What if you give the test and then repeat it after 6 months of training? There's the difference, 17%. And the last slide I want to show you is that this translates into real improvement in school-administered tests of math and reading achievement, not administered by us, the same ones that show and document the achievement gaps in this country related to poverty and race, these same tests. This is a math test. What's expressed here in green are the proportion of children who meet proficiency, yellow, the proportion just below proficiency, and red, the proportion of kids in big trouble, way below. This is a whole district score, fall to spring. This is a class in a poverty area school that got our program, fall and spring. In the spring score, 92% of the kids who did our program met proficiency. The district had never seen that level. Thank you. Sorry for going over.